Hi, my name is Jerry Chow. I'm an IBM fellow and the director of quantum systems.
Lovely. Thank you so much for talking to us, the Economic Times and the Times Group. We're talking about Quantumly. I spoke to Chetan also, and the discussion you had. How was the experience today at the TiEcon?
It was great. It was a good discussion. I think, it's good to be able to certainly introduce a topic like that, especially in a conference like this where it's very AI focused, because it's very relevant for people who are thinking about where computation is going to really have quantum be part of their minds as well.
Yeah, I think there is this distinction that people quite don't understand, including me, on where quantum steps in.
Yeah.
It seems like it has its own limitations. Mm-hmm. It's not for everything.
Right.
What are some of the use cases where quantum can be used?
Yeah, so I think a good place to look is really areas where we know that classical computers that we use today really struggle. And that includes problems which grow exponentially with their problem size. So things like molecular structure problems, finding the lowest energy levels or ground state energy levels of molecules. We know that those actually end up using probably the world's most amount of high performance supercompute today, right? And it's one which we are really excited about using quantum for. Others are really types of problems where there's some type of inherent structure that makes the data processing very, very challenging for classical computers. A good example for this is factoring numbers, which is behind encryption, right? And then others would be like optimization and search types of problems.
Lovely. And what are the challenges you're facing in that? Is it too much of energy usage, or is it how does that work within the QPU? Is that the
QPU? Yeah, the QPU. I mean, at IBM, we actually make some of the world's most performant QPUs today, and we're deploying them all around the world. A big part of where we're at today is we're at the scale where we can actually run certain quantum circuits on them, quantum circuits being the type of computation you can run. We can run them at a scale that you cannot actually exactly simulate them with classical computers, right? So, but then I didn't say anything there about how useful it is for a particular problem. And so it's kind of in this explore it and find its application kind of regime. Which is actually what happened in classical computing for many years also. But it's like we're at the point where we have this useful tool, or we want it to be useful, and people need to leverage it with the rest of their compute platforms, AI, high performance compute, and find what problems can it actually be leveraged for.
Lovely. And in education itself, I wanted to deviate a little bit. I guess quantum at some point in time is associated with some bit of physics and some bit of math. It's about time that these courses now change and become a core on its own, like quantum has its own course, and AI, a different aspect of it becomes its own course, like for example, biotech engineering, stuff like that.
Yeah, no, I think it's a really interesting direction. We've been very committed to educating the world. We have a lot of open content available on our YouTube through our open source software development kit, Qiskit. And I think that there's parts of it where you don't necessarily need to know the underlying physics, and you can actually approach it from the more like a computer science perspective of learning this is actually how you build a quantum circuit. And there's an entirely very rich way of trying to learn how to leverage it, right? That doesn't require needing to know some of the fundamentals of entanglement and so forth.
Love that. Thank you so much, Eric. It was such a pleasure talking to you. Thank you so much.